Okay, so in this video I do a quick summary about this chapter. Obviously you can read more on this from your lecture notes. Okay, so chapter 10 is about wave properties of a particle. So in this chapter you will learn about wave particle duality. Okay, you have one equation for that, and then you have electron diffraction, and you will learn about Davidson experiment as long as basic concept of electron microscope. Okay, so in this chapter actually you only have two formulas. Okay, one is lambda equals to h over p, another one is lambda equals to h over 2 mev. I just write down. So another equation is lambda equals to h over square root of 2 mev. Okay, this is the two formula that are given inside the formula sheet. Okay, the learning outcome for the first subtopic is that you need to be able to state wave particle dualities and use the de Broglie wavelength. So this is actually the de Broglie wavelength. So you have the derivation, you can check with the lecture notes, and then it ends up like this one with this equation, lambda equals to h over p. So h here is the constant, Planck constant, 6.63 times 10 negative 34, and p there is actually the momentum. Okay, since we are talking about the momentum of an electron or any particles, so p is equals to mv. So this is basically how you want to calculate wavelength for particles. So basically in this chapter we discussed that particle has a wavelength. Any particle actually has a wavelength. If you want to find the wavelength for the lights or photons, you have to use lambda equals to E equals to hc over lambda. Okay, that one comes from the previous chapter, but this one we want to discuss if a particle that has a mass, you can actually calculate the wavelength. And then this equation actually give because it has a lambda, it actually says that it shows the properties of wave, and the fact that it has a p shows that it has the properties of a particle. Okay, so this is what we call the wave particle duality. Okay, so this is some of the ideas lah. So here you have electrons, lots of electrons. Okay, so supposedly if electron behave as a discrete particles with no properties, okay, they will pass through one or another two slits and strike the screen. So it will show a pattern like this if we treat electron like particles. Okay, but that does not happen. That in reality the screen will give you the interference pattern. Okay, so because of this, it actually shows that even though electrons are particle, but it behaves like a wave. Okay, so that's why you have the wave particle duality, where wave can exhibit particles like characteristic and particle can exhibit wave like characteristic. Okay, so if you are talking about particle, so that particle can behave like a wave, and at another time it can behave like a particle, but it wouldn't happen at the same time. So either one, but it can interchange. Okay, this is more proof. Okay, so this is the actual data. So if you have 100 electrons, you wouldn't see the pattern yet, so it seems like a random. Okay, after 3000 you can see like this is like slight dark, still not too obvious. But if it is continue after 70,000 electrons, this is the actual data, you can see the clear, bright and dark fringes. So constructive and destructive interference. Okay, so again, even though this is a particle, okay, you can see the interference pattern, and this patterns is obvious for electron because the mass of the electrons itself are very small. Okay, when the mass of electrons is very small, then the lambda is actually quite big lah, as compared to normal object like you yourself. Your lambda would be very very small, so to find this pattern is really really difficult. Okay, so you have actually the first discoveries from the Davidson experiment. So this is actually similar setup to the actual one, and everything here actually done in vacuum. Okay, the main reason is because the electron is very the mass of the electron is very light. So if you want, you cannot interact with any other particles now. That's why it happens in vacuum. So heated filaments emits electron. So basically, filament, when you heat up, electron get excited and then emits electron, and then it's accelerated through electrons and directed at crystal. So this part, okay, where it is actually applied some potential. So initially there's no energy, like E is equals to potential is equals to 0. Applied potential over here, those potential then becomes the kinetic energy. Okay, so the whole, like if you apply 10 joule of potential, that 10 joule of potential becomes kinetic energy. So you have velocity. Okay, and then it is actually directed towards the nickel crystal, and then a detector then can detect the pattern. Okay, so what happened inside the nickel crystal is that actually the crystalline structure of the nickel itself have like a diffraction grating. Okay, now I want to discuss about the conservation of energy of potential and kinetic. So U is equals to K, okay, because the whole potential now becomes kinetic energy. You know that U is actually equals to QV. Since we are talking about electron charge, it becomes EV. Then K is equals to half mv square. Okay, notice that over here is small v and this one is capital V. This one, capital V, represent the potential, volts, and V here represents speed, velocity. So because we want to relate with momentum, and you know that P is equals to mv. Okay, this one is from previous semester. And if I want to write this as V, then I will have the extra V, right? So this one is like mv mvv. So if I want to have P square, then basically I have to have mv, no? I have to multiply by m on both sides. So here I have mev. Okay, remember E here is the elementary charge, right? E equals to 1.6 times 10 to the 19. 1 over 2 m squared v squared. Okay, m squared v squared means this is a P squared. I can bring 2 to the other side, and P here is actually equals to okay, P here now is actually equals to square root of 2 mev. Okay, and then if you remember previously we have de Broglie wavelength equation, h over P. I can write this one as h over square root of 2 mev. So these are the two formulas that are given inside the formula sheet. Okay, and then obviously EV there you can write in terms of K, so it becomes 2mk. Okay, and then if you are talking just the energy, so again you can write this one as 2me as well. So that one is just the energy. Okay, but normally we use the kinetic or EV here. Okay, so because of this equation, it shows that actually you can control the lambda for particle. Okay, since you can control the lambda, and then actually you have a relation between lambda and resolution, where lambda is inversely proportional to the resolution. So basically, as long as you can have high enough potential, you can produce low enough lambda, and as a result you can have pretty much a very high resolution microscope. So this is an example of scanning electron microscope. Okay, so electron microscope have a different type, like transmission electron microscope, scanning electron microscope. So you can look through your notes for that. Okay, this is just example. And then in your notes they give you like advantages. The disadvantages is like it's quite expensive. Okay, costly to maintain, and then you have to do pre-treatment of the samples, and obviously you have to do it in vacuum and so on. Okay, there's drawbacks as well and advantage, but the main advantage is that you can get a very high resolution as compared to optical microscope. Okay, as a conclusion, as a summary, the last part, in terms of calculation, which is what they might ask in exam, you have two formula. Lambda is equals to h over p, and lambda equals to h over square root of 2 mev. Okay, and this one you can write as mv as well, which is momentum multiplied by velocity, and this one you can write in terms of kinetic energy. So most of the time you just have to use this formula.